PhD in She did her PhD in stochastics and stochastic processes in Ukrainian National Academy. After that, she moved to other area doing some geostatistics analysis. She was the head of division at National Academy of Ukraine on geostatistics, and but she still continues working in stochastic processes. And several years ago, she moved abroad, and so she had a couple visiting positions in Italy, Germany, and now she is University in Jena. She works on diffusion processes with membranes, limit theorems, and many related areas, and also on some applications to some physical problems. Olga, you are very welcome.
First of all, I'd like to thank Andrei for this great opportunity to be here in Australia. This is my first visit, and to give a talk, to visit a few universities here. So thank you very much, and it's my pleasure. I'm going today to talk about one interesting problem, which is not pure mathematics. Namely, it's come from physics, and it is now one of the problem many people deals with. They try to build a artificial sun. So what is the artificial sun? Roughly speaking, it's a source of pure energy, and which will work almost ever. And how does it works? There is a device which is called tokamaks, and this can be imagined as a torus with a source of energy in the middle. And then there is a turbulence inside. It is the turbulence confined in one torus, and the energy by turbulence goes from the hot center to the boundary. There are many problems, so until now we have no artificial sun, and one of these problems, and in intermediate region, something between the center and the boundary, occurs transport barriers, which are called also zonal flows. These transport barriers is a laminar, almost laminar flows, which is perpendicular to the main transport direction. I mean, from the center to the boundary. These layers are very thin and with plasma layers, and they are ordered, have no more turbulence, and they significantly reduce this dispersion of heat from the center to the boundary. The mechanism behind the formation and dynamics of this barrier are still under active investigation, and this nature is not clear. And we are not address this question, but we just want to build a model of this barrier. So first of all, about the turbulence and how we are going to consider this model. Let us go back to usual transport heat transfer model. So what is known? The simplest transport heat model is when the heat is transported just by a flow with a velocity v. Then we have the following differential equation, and the temperature field can be defined from this equation. Usually, so not usually, but often, people also consider additional term which is derived by the diffusion, so microscopic motion. Then in this equation, an additional term appears, which this term has now the second derivative, and the coefficient which is called thermal conductivity. Now we have the spread of the heat both because of the drift, so the velocity field, and diffusion. When the velocities of these liquids or something else is high enough, of the flow is high enough, this means that it has a high Reynolds number, the velocity field becomes unstable. This occurs as small perturbations originating from noise, and often this noise have a, and usually this noise have a, random structures, and they originate from this, okay, maybe from boundary effect for and so on and so forth, some noise, really noise, random noises, and external forces. And if we consider the Navier-Stokes equation, we have a nonlinear terms in this Navier-Stokes equation. As a result, the initial velocity fields, which we have in initial, have an additional term, became an additional term, which is driving for this turbulence motion. Let me try to describe the model of this turbulence motion and try to build, as is usually done, this turbulence velocity field. Yeah, and okay, and usual procedure, I'd like to say about some word about this. So I try to build a turbulence velocity field, and after after passing to the limit, this additional turbulence velocity field gives usually additional diffusion term in this diffusion equation. So we start from the velocity field, not usual velocity field, but velocity field driven by random components. And in limit, one obtains usually the second order member in this equation, which means that we have the additional diffusion coefficient. And it's called usually the turbulent diffusivity. So let me introduce my stochastic fluid model. So now I'd like to build this turbulence velocity field. I'd like to consider something like torus, because there's like a tokamaks nature. So the domain I will consider is a domain of this kind, -1, 1, 0, 2p. Oh, okay, non-symmetrical, sorry. What I have the special in this, so the model, okay, it's known how to models this velocity, turbulence velocity fields, but what I have non-usual, I'd like to build the barrier, this barrier which arrives in this tokamaks, and I want to consider to build this barrier at the point, not at the point, but at the line x is equal to 0. So, unformal, I have a high temperature here at -1. Then the temperature disperses somehow up to this barrier. At this barrier, it must drop very fast. and then it goes to 0 at the point 1. This will be the boundary of this torus, and this will be the middle point of this torus. This my model. I'd like to consider this my model very informal. Formally, I will consider a velocity field u in this domain such as that we will consider divergence velocity fields. In vertical direction, I have a periodic condition, and this is very natural because I want to consider torus. I have slip boundary conditions. That means that now the heat cannot go through this boundary in this direction. I'd like to consider a transport barrier around x equal to 0. Some word how I can going to build this barrier. So everywhere I'd like to have this velocity field, but this velocity field vanishes around 0 because I have this barrier, so I have these laminar flows. And I represent this barrier with a smooth function he, which looks like as follows. We have epsilon and 2 epsilon. Let us out minus 2 epsilon, it will be just 1. And then it will be smooth and goes to 0, such that at 0 it is equal to 0. When we product the turbulence field on this function he, we obtain that we have turbulence fields everywhere except the neighborhood of 0. And the neighborhood of 0, turbulence field vanishes, and we can have something else, say this laminar flow. This is usual representation. What is the idea of the modeling the turbulence flow? This turbulence flow has many vertices of eddies of different spectrum. So this will look like more or less as a Fourier series representation, but in real after over the real field, not complex field. So what we have here, C will be some coefficient. I defined it later, but it will be constant. Here I have this function from Fourier representation, namely it will be sinus and cosinus, and I consider nabla perpendicular. This is, I define this such that this will be non-divergence field. This sinus and cosinus, I multiply by he to make this field vanishes in the neighborhood of 0. And then I multiply this by W with the point. This can be roughly so this represents the noise, and usual physical procedure gives follows. We consider Wong-Zakai approximation, so instead of the bad trajectories of Wiener process, we consider something more smooth, or not more smooth, but something with better properties. For example, this can be discretization, or then maybe it with some kernels, so to avoid the bad properties of the Brownian motion, to make sense of this derivative, because for Brownian motion, this derivative with respect to t is doesn't defined. But I'd like, of course, obtain in passing to the limit the usual trajectory of the Brownian motion. So some words about these coefficients. We define the coefficients such that for every n, this sum has only the finite number of items, and also such that we have some using normalizing. So we defined this coefficient in this way. It's not very important. You can imagine just that we have here the finite sum with finite numbers of members of this sum. And K now is a two-dimensional vector of integers. Now, I'd like to substitute these velocity fields, turbulence velocity fields I built into the equation as follows. So this is, it looks like an ordinary diffusion equation. I have here diffusion coefficient, and I have here some velocity field, so some drift. But now you remember that this drift is not usual, but it have inside noises, summation over noises. But I'd like to consider this problem. So because yes, really I have a flow inside this, say, tokamaks, and there exists a very small diffusion, and there exists this turbulence fields. I add a boundary condition, as I've already said, in the -1 it will be some temperature, and I'd like to obtain in 1 0 with this drop at the point x equal to 0 because of my barrier. So this is a substitution into this equation. It is well known that if we consider it is again von Sakai approximation, and if I consider this W with point as approximation of Brownian motion, I must put here a Stratonovich integral instead of eta because it preserves the operation, and this is well-known fact. But I intend to consider the usual equation with eta integration, and then my equation with Stratonovich integration can be rewritten in eta form, but I obtain here an additional term, which is called eta Stratonovich corrector. We want to study in sequence two limits. First of all, I'd like to passing to the limit in this equation when capital N tends to infinity. As I've already said, this is a usual construction of turbulence flow. Now I have this, say, Fourier sum. Passing to the limit, I expect to obtain the additional diffusion term in this equation. This will be the first one. Instead of this strange now, this is a partial stochastic differential equation, and if I passing to the limit when n tends to infinity, I hope to obtain, so this is the usual way, I hope to obtain the usual diffusion, usual differential equation with two diffusion coefficient, K epsilon, which I have now, an additional diffusion coefficient, which is burned by this turbulence flow. So this is the first limit. And after that, I obtained the equation of this form. This is a new equation I obtained after the passing to the limit. So this is my new diffusion coefficient I obtained because of turbulence. with some limit operator I show you later. And the second, you remember that I defined all the coefficient with this function he, because I'd like to construct this barrier in the middle, so the point x equal to 0. This function he is smooth, but I like tends to the limit. So my functions he are something like this. Passing to the limit to epsilon, this is to epsilon. I'd like to obtain a sharp barrier, not smooth barrier, but sharp barrier, and this will be the second part of my my talk. And I'd like especially talk about the second part because this first diffusion limit is more or less standard in the theory of turbulence. The only difference I have is the presence of the barrier. So the proof is not standard because of this, but more or less it's so we somehow must rewrite the usual proof, and this is some technical and not very simple work, but it's not from my point of view, it's not so interesting as the real limit which we obtained in the second part. But in any way, I need to at least say something about the first limit, and this is the next small part of my talk. The diffusion limit. This is a theorem according to which, starting from the temperature field which defined by the equation with this turbulence velocity field, I obtained in L2 and in the space of consider some test functions phi. It's not okay. A epsilon is not defined here explicitly, but it's some class of test function. I have this convergence, and the limit temperature field is the solution of the following equation. Now it's just a partial differential equation, no more partial stochastic differential equation. And here I obtained really the additional diffusion term. So no more this velocity field which acts on the first derivative of the t, but I have this additional diffusion term in this equation. Further, I will suppose that the diffusion coefficient itself is very small. They are both very small, both diffusion and turbulence diffusion coefficient. But diffusion coefficient is much more smaller than the turbulence diffusion coefficient. So turbulence is the main force now which driven this equation, which driven this flow motion. And again, I must add the initial condition in -1 and 1, the same initial condition, and some the boundary condition, sorry, and some initial condition. What about the barrier? I'd like to explain you, to show you implicitly that really having the function he and passing epsilon to 0, we obtain a sharp temperature barrier. So let's consider, for simplicity, let's consider the stationary problem associated to the diffusion limit equation of the previous theorem. So it's the same equation, but without the derivative with respect to t, with the same boundary conditions and periodicity in y direction. The function he now depends only on x. So this first equation has a coefficient which are constant with respect to y, because these are constants, and he depends on x. So the solution must be constant with respect to y. and we can find it implicitly using acting as following. So solving this and using the boundary condition, I obtain the solution in this form, and I can find this function phi. So I can solve this equation implicitly. And what we have if we make, we can consider also the concrete function he, which is more or less satisfy our assumption on function he with maybe minimal deviations. And what we see, if epsilon in at this formula is equal to 1.2, we have this magenta profile. So we have here really the drop of temperature, but not very fast drop. If we have no barrier at all, so the function he now is equal to 1, we have just a linear drop of temperature from left boundary to the right boundary. And when we consider epsilon, which is smaller, say 0.01, we obtain, the simulation shows that we obtain the sharper barrier. So really our model works, and if epsilon will tends to 0 in this function he, we expect to obtain really a sharp barrier at this level x equal to the, x equals 0. Okay, so but this is numerically, and which process of what we obtained, what we obtained, namely when epsilon passing to 0 with respect to epsilon. So I will consider this problem in the term of stochastic differential equation. It is well known the connection between partial differential equation and stochastic differential equation. Namely, if we have partial differential equation, I mean heat equation, then corresponding stochastic differential equation has the following form. Before dt stays drift coefficient, and before the Wiener process stays the square root of diffusion coefficient, roughly speaking, because yeah, we have here two-dimensional case, but okay. So this equation corresponds to our partial differential equation. And also we must suppose that with respect to y, we have this periodic condition. So we regard the point y plus 2pn and y as equivalent. Suppose that initial condition is smooth enough, then the solution of this problem we are interested in, I mean the problem in terms of partial differential equation, can be represented according to Feynman-Katz formula as follows. We have here two members. First of all, we consider the very important moment, stopping moment tau epsilon, which is the first moment when the process reaches the boundary, so -1 or 1. Before this moment, this process can, this temperature profile can be defined as the expectation of initial condition in which we substitute the process x epsilon y epsilon, which is the solution of this stochastic differential equation. After the moment when the process reaches boundary, we obtain this second member, which is t plus probability that at the moment when the process reaches the boundary, it reaches the point, first time reach the boundary, it reaches at the point -1, not at point 1. Here must stay the expectation of the x epsilon tau epsilon, but the second member in this expectation is equal to 0 because at point 1 temperature is equal to 0. So we have only this second member. And so if you will consider again the stationary problem, so such that t tends to infinity, this first member vanishes because it's well known that with good coefficient, this diffusion process reach the boundary in a finite time. And for a stationary solution, we obtain only this second part of this solution. So for stationary problem, temperature profile, stationary problem corresponding to partial differential equation boundary, initial boundary problem for the partial differential equation, the solution is defined just as a second member here, t plus and probability to leave the region from the left boundary. So if we find this probability for the solution of this stochastic differential equation, leave the boundary from the left side, then it means that we defined this temperature profile. And then we can, passing to the limit when epsilon tends to 0, we obtained what we need. So now my aim is to find the solution of this equation, namely when epsilon tends to 0. If I find the solution to this equation when epsilon tends to 0, then I can substitute the limit process here and find the limit temperature profile. So what is the limit of the solution of this equation when epsilon tends to 0? And this is the second part of my talk, and this is interesting by itself. To make this equation easier, I'd like to kill this coefficient before the Wiener process to obtain here 1 and here 1. And there exists a standard procedure how to do this. To do this, I use time change as follows. Consider such an additive functional and obtain the strictly increasing function such that exists inverse function. And after considering the new process from this inverse time alpha t, I obtained the new process, which, as I wanted, has now the diffusion coefficient 1. It's easier for me to, now I have just a Wiener process. This process behaves as a Wiener process everywhere except the neighborhood of 0. And the neighborhood of 0, it has some strange drift coefficient here, which depends on this function he, and but the diffusion coefficient are constant here. And I'm interested in the probability for this process to leave the domain -1, 1 through the left boundary. But my change of time doesn't change this probability because the process leaves this area earlier or later because of change of time, but again under the same boundary. So for me, it's okay, and it's the same to find this probability for this new process or for the initial process. Here I have a new Wiener process. And again, as I already said, but one more assumption. So I suppose that this relation converges to infinity as epsilon tends to infinity. This means that they both are very small, but kappa t is much greater than kappa epsilon. And this relation tends to infinity when epsilon tends to 0. We will show that the dynamic of X tilt exists and is non-trivial as epsilon tends to 0. Of course, for me, the dynamic of X tilt is interesting now because with respect to Y, I have very usual dynamic as a dynamic of ordinary Brownian motion. The next section is spoiler. I'm going to represent the limit process which I obtained. This process was represented by independently by two scientists, Pilipenko and Leger, absolutely independent at the same year, 2016. And okay, but to introduce this I'd like to introduce what I'd like to consider informal first. I'd like to construct a Wiener process, which is just a one-dimensional Wiener process, which is just a Wiener process everywhere except 0. And at 0, its behavior is looks like as follows. Imagine that you sit in the room and you watch a mosquito who try to go through a screen on your window. It is here, and it beats the screen 1 time, 2 times, 3 times, and so on. And if the screen is not perfect, after some time, he can find some defect in the screen and go through the screen inside. And it's interesting that if there is another room here or all the space, the time in which this mosquito goes through the screen doesn't depend on the time it's spent in all this space, and depend only on the number of attempts to the mosquito to beat the screen. So it depends only on the time mosquito spends in the small neighborhood of this screen. This is informal subscription, informal motivation for process Brownian motion with some special membrane I intend to consider right now. But what is membrane? Let me recall some facts. I start with a very simple object, limit symmetric Brownian Bernoulli random walk, or drunkard walk, as it calls sometimes. It means that a drunkard returns home after a long evening, and he make every tact of time. It make 1 step to the left with probability 1/2 and 1 step to the right with probability 1/2. We model this with a random variable which is equal to 1 with probability 1/2 and -1 with probability 1/2. And then after n steps, we have an object which is a sum of the step at each the n steps. So every item here is 1 or -1, and here we can see the typical trajectory of this random walk. Of course, it's a random object, and it is well known that under appropriate scaling, this symmetric random walk, symmetric because these probabilities are the same to go to the left and to the right. After the appropriate scaling, this symmetric random walk converges in distribution to a Wiener process, trajectory of Wiener process at 0, 1, when n tends to infinity. Let me consider again the symmetric Bernoulli random walk, but make it worse at 1 point, at 0. Namely, I consider a new probability alpha. A new probability alpha, such that the process go to the right at 0 with probability alpha, and go to the left with probability minus alpha at 0. It means then when this when this random walk reaches the point 0, we toss the coin and can go to the right with probability alpha and to the left with probability 1 minus alpha. Namely, I need today only the one object when this alpha is equal to 1. So this is so-called Brownian motion with reflection at 0. So when the process reach 0, it instantaneously reflected in the positive direction. It means that instead to go to the negative direction, it goes to the positive direction, and the trajectory is a mirror of the trajectory with respect to the y-axis. Under the same scaling, the limit of such a process is so-called Brownian motion reflected at 0 into the positive direction. This process can be described in different ways. And one of the ways is that this process is a solution of the famous Skorohod's problem. It can be represented as a sum of Wiener process and some additional functional L plus. This functional can be represented explicitly as follows, as a minimum of minus minimum W and 0, W and 0, or it can be represented as follows functional of the process W plus. The trajectory of such process belongs to 0 infinity if the process starts from the positive semi-axis. And in the same way, we can define the Wiener process reflected at 0 in the negative direction. This is a representation for this process with the reflection into the negative direction. And I have now all to represent the Brownian motion with the hard membrane. I need additional object. This is a Markov chain with two state space, with state space of two consisting of 2 points, -1 and 1. And the intensity of going from -1 to 1 is beta minus, and from 1 to -1, beta plus. It is well known that then this Markov process jump into another position after the exponential time, which has parameters beta minus and beta plus correspondingly. Let us define two random variables which doesn't depend on Wiener process we have, and which has exponential distribution with parameter beta plus and beta minus correspondingly. And we define the process with hard membrane as follows, as a solution of this equation. So what we have here, initial point, Wiener process, this so-called local time I represent on the previous slide, and I also can represent here. This local time is an additional functional of a known process x. It can be imagined very informally as a delta function at 0. So, except 0, our process is just a Wiener process. At 0, we have this local time, so it have that local time is non-negative, we can see here. So it obtained an initial impulse, like a delta function at 0. And here we have a coefficient n. N is equal to 1 or -1, this is our Markov chain. And this n changes sign, yes, after the exponential time. What it means? Suppose that this process starts at some point which is greater than 0. Then it behaves like a Wiener process with reflection into the positive direction until, because now n is equal to 1, and we have this equation which is exactly the equation for Wiener process with reflection, until the time when this coefficient, so it means this random variable, this coefficient will be equal to this random variable with exponential distribution. When it became -1, the process switched instantaneously into the negative semi-axis and start to be the process with instantaneous reflection at 0 at negative semi-axis. So it leaves at positive semi-axis, is waiting until the time will be as high as exponential random variables, then switch into the negative semi-axis, live there until again this another random variable, this local time will be as great as this another random variables, and so on. It means that the process can go through 0, but not very fast. He wait a time, an exponential time, like these mosquitoes near the screen, and then go through 0 to another part of semi-axis, and then back, and so on. And so this object I've just represented, its occur is a boundary object for our equation, our stochastic differential equation I represented earlier. And I will consider it is very important theorem how we can obtain in another way this equation with hard membrane. I consider a sequence of stochastic differential equation. This is just a linear process, and here I have a drift coefficient. Suppose that this drift coefficient, this sequence of drift coefficient with respect to epsilon, has a compact support. Each of them has compact support on minus epsilon epsilon, and such that it is greater than 0 from the right hand side and less than 0 from the left hand side from 0. And we are interested in two probabilities. Let me consider the first one. The second one is absolutely. So for this process, for one-dimensional process, X, I consider 3 points, epsilon, 2 epsilon, and minus epsilon. And P plus epsilon is a probability for this process starting from the point epsilon, reach minus epsilon earlier than 2 epsilon. Reach minus epsilon earlier than 2 epsilon. So it means that it must pass 0. And analogously, we can define the P minus epsilon. This probability defines the convergence of initial process to the process with hard membrane. If this probability P plus and P minus divided by epsilon gives a limit between 0 and epsilon when epsilon tends to 0, then the solution of this equation converges in distribution to Brownian motion with a hard membrane and parameters B plus and B minus. We use this theorem to obtain our result. And I formulate my main result of this second part of my talk. Yeah, I know. I just maybe formulate. So I return to my equation, namely the first coordinate of equation. I have here some A epsilon, some drift term F epsilon. I defined a function he now in the special way, namely as a function like epsilon in power, x in power alpha, with some fixed parameter alpha. And so it is the form I need. And this form is given by this parameter alpha. It's something like this. And here will be 1. And we have different cases. Assume that the relation between kappa t and kappa epsilon tends to infinity as epsilon tends to infinity, and chi is some constant. In the dependence of how fast they tends to zero and so on, when epsilon tends to zero, we obtained either Brownian motion with a hard membrane and parameter, which now defined by this integral, and which is symmetric. So the probability to switch from positive semiline to negative semiline and back are the same. Or at some situation we have just a Brownian motion reflected at zero with non-permeable membrane, or just a Brownian motion without a membrane at all. And in this situation, when we have the convergence to a hard membrane, so in this first case, I have no time to speak about the proof. In this first case, we can find this process to go through the left boundary earlier than through the right boundary. We need this as a solution for the temperature profile, because for the hard membrane it can be found. If we know the boundary process, we can found this. And so from this corollary, we obtained the solution T of boundary problem for partial differential equation, for initial boundary problem of partial differential equation I consider. So that's all.
Okay. Thank you, Olga. So first, probably people from online audience, if you want, just unmute yourself and ask questions, please. Okay, maybe from here, questions. Okay, so I have a question about the first part.
Oh, sorry, he has a question also, but no problem. Yeah.
So it's not torus, it's all contained by magnetic field.
Yeah, again here.
Sorry, like the torus is all the heat and whatnot contained by a magnetic field in the torus?
Yeah, yes, exactly.
Okay, so the question was
confined to fluid plasma inside.
How plasma is just like restricted from moving away and just by magnetic. Okay.
Exactly. And another question.
Okay. Is this going to help the physicists help them understand the mechanism, like if a mathematical model, that sort of help them probably focus on various aspects? Which would lead to that?
Yes, we hope so. So the idea is the interchanging between physicists and mathematics. But it's just our first step in this way. It's our first model, yeah.
Because they want to keep basically they want to keep that equal, energy in, energy out, and then increase, so it flows very well.
Because the story is as follows. Flanders deals with this plasma and another problem, and so the problem with connecting with turbulence. And it occurs that it was one of the problems for a long time. He was thinking about this barrier, how to construct them. And from our side, me and my colleague Andrei Pilipenko, initially from Ukraine, we dealt with the different type of barriers and diffusion with barriers for a long time. And so we, at one point in time and space, we met each other. And Flanders says that maybe it's a good idea to to make that really this barrier can represent what the reality of things in this model.
Okay, I have a mathematical question about the first part of your talk. So you consider the heat equation. If you start considering more general equations with maybe with fractional derivatives in time or whatever, is it possible to produce some results? I understand that maybe not all machinery is available, but how far you can move in this direction?
What do you mean now as a result? So
yeah, so first you just represented some solutions, yeah. So when for example you consider this velocity or whatever specific time, yeah. So if you do the same for other types of equations, does it make sense?
At least numerically, I think so. Yeah, I don't know about the second part, for example, this convergence to some concrete process, because I don't know what this process can be, because this process with barrier can be constructed, and we have done something, for example, even with Arsinger, with barrier for another process, not usual process, from fractional motion and so on. It's not very easy, but so people try to do this, really, to construct this.
Okay. Any other questions or comments, please? If not, so let us thank Olga, and we will finish seminar at this point. Have a good day. Bye.
Bye.